This is Friday, May 6th, and we're doing the second lunchtime CST review. And what we're going to do is take a look at a question that was brought in that goes back into last semester's work. And that was on a review that Mrs. Jahshan's giving. And the first one that I want to point out to you is the carbon-14. You want to write the isotope symbol for carbon-14. And when you do that, you got to remember that your atomic number is on the bottom. So C is on the bottom, and 14 would be on the top. So if you look on the periodic chart, you see where carbon is, number 6. Okay, that 6 is what goes in the bottom. On the top, you got a total of the protons plus the neutrons. Okay, so if you wanted to know how many neutrons you had, what do you think you're going to do? Yeah, because the atomic number is the protons. So we subtract 6 from 14, 8, right? So that's our neutrons. You probably knew this at one time, but you haven't used it for a while, and so it's not making sense for you.
Is that the isotope?
This is this is isotopes, and all of the elements up there are all isotopes. They're the average isotope of all of the isotopes for all of the elements, okay, including their abundance. Because you got to know what the percentage is of each in the abundance to be able to get an average overall. Okay, so carbon-14 is made like this. Now, what was the other one you were interested in?
The second one?
This here?
The oxidation states.
Oxidation states.
Right under the isotope.
What chapter is that in?
Right under the one that you...
Oh, okay. I had the table. In here? Come over.
Identify the oxidation states for elements in 1A, 2A, 3A.
Oh, okay. Identify the oxidation state, the states of elements in 1A. Okay, 1A is, if you'll open up the inside back cover of your textbooks, you're going to see what state each of those elements is in. Inside back cover. Inside back cover. Back cover. That's the front. Okay, in the back, you've got a little symbol in there for each of the elements. Okay, let's look at 1A. 1A is this column. And so as we go down 1A, we're going to see that this guy is what? Yeah? You know what the little balloon means? That means it's a gas. Okay, and where are we going to see that? We're on the right page to see that. Okay, see, the balloon is a gas. The liquid is a little drop of water type looking. Your solid is a cube, and those that are man-made or synthetic are the circles. Looks like almost like a little target. Okay, folks, I'm not going to keep your name on this sheet for extra credit if you're not writing stuff down, because if you're not writing stuff down, this is going in one ear, not the other. Okay, so this guy would be a gas, and how about all the rest? They're all solids. Okay, I think that's what she's after. That's what she wants to know. Okay. So, oh, I'm sorry, oxidation states. Oh, I was thinking states of matter. Oxidation states. Okay, this is really easy. You go to the column number, and it tells you the oxidation state. +1, +2, +3, +4, +5, +6, and 7, and 8. Now, those are how many valence electrons they have. The oxidation state goes like this. Column 1 is a +1. Column 2 is a +2. Column 13, or 3, is a +3. 14 and 15, they're all over the place. So we can't generalize on 14 and 15. But 16 is always going to be a 2 minus. 17 is a 1 minus, and 18, there is no oxidation state because they don't form ions. They don't react, they don't do anything. Noble gases have their noses in the air. I'm too good to react with anybody. I am a noble. Yes. That's the dudes here in column 8. All right, they're always loners. You might want to write this down too. I want to give you some other stuff that's going to help you with this. Let's open up a notebook file and do it here. We'll go to this guy. All right, watch this. Okay, column numbers. 1, 2, 3, 6, 7, 8. And oxidation state is going to be 1, 2, 3, and then we're going to have 2 minus, 1 minus, and 0. No oxidation state. Now, why are they what they are? It all has to do with getting to look like a noble gas. If this guy loses 1 electron, he's going to look like a noble gas. So let's look at his valence shell. He has 1 electron. Okay? When that guy goes away, and he's balanced, isn't he? Yeah. Equal number of electrons and protons. I'm going to take that guy away. That's a 1 minus charge. Just left. Now what do we have? My minus pile just got smaller than my plus pile. So what's the charge? Positive 1. Yeah. Okay. On this guy, I'm going to take away 2 electrons. 2 electrons. Take 2 away. What's the charge? Yeah. The electron pile goes down. The proton pile stays the same. It can't change. Proton pile is fixed. If I change the size of the proton pile, I've got a different element. Okay? So, 2e, I'm going to be, when I take those 2 electrons away, when I take these 2 electrons away, I have just become 2 plus. And now when I take away 3 electrons, I'm going to be a 3 plus, right? So this guy is a 2 plus, 1 plus, 2 plus, 3 plus. Now, why do these guys go negative?
Did they add electrons?
Yes, they add electrons. So proton piles stand the same. They were neutral, and they say, give me an electron, please. I got to have an electron. Why do I want an electron? To be a noble gas. Oh, yes, I'm feeling so great. I'm a noble gas. I can have my nose in the air now. Woo. Okay, so if I get 1 extra, I'll be a negative 1, right? And look at the guys in column 17 or column 7. They're 1 away from noble gas. So we're going to add electrons. We add 1 electron, and we have become negative. It's inverse type thing. Okay?
So above it, you add 2 electrons?
Yes, we're going to add 2 electrons, and we're going to go to negative. Why? Because in column 16, if we look at column 16 up there on the chart, we're going to see that starts with oxygen. And let's put it on here. Oh, won't see it. Anyway, on column 16, we're going to add 2 electrons, and we're going to look like noble gases, no matter where we are in the column. And now let's go to column 5. In column 5, this works most of the time, but it's not reliable because sometimes in column 5 we're going to add electrons, sometimes we'll take them away. Go figure. Okay? So they're switch hitters. That's why we don't have them as a good ironclad rule here.
When it's too negative,
Uh-huh.
it becomes plus. Does that mean the positive is going up or the negative?
Positive never changes. It's always the electrons that change. Remember, if you change the protons, you have a different element, because that's how we define the element, is by its number of protons. Okay? So for these guys, as we're losing electrons, we're going positive. And we're losing those electrons so that we will look like noble gas. That's all there is to it. And we're always talking about valence shell electrons. Okay? And VSEPR, y'all remember what VSEPR is? Valence shell electron pair repulsion. Has to do with bonding and how molecules are made and what their shapes are. VSEPR. That's something you're going to absolutely see on the CST. That is big, big, big. Very, very big. Because so much depends on it in chemistry. Okay? So VSEPR, valence shell electron pair repulsion. Okay? So that guy's important. And here is everybody feeling solid on this? If you're not, raise your hand. Because that's also referred to as your oxidation states, or the charge on the ion when we form an ion. Okay. And as long as we're on ions, yes.
So it's like a element like the O, and then if it has like
Okay, oxygen.
Like O plus 3, does that mean it's
There's not going to be a 3 plus on oxygen ever. Oxygen will never lose electrons. He's not going to go positive.
Okay.
See, oxygen's in column 16. He only needs 2 to get to noble gas. So he's not likely to ever do anything but 2 minus.
There's this element in my paper over there. It's something 3 plus 3.
3 plus. Yeah, that would be guys in column 13.
And they said to find the photons and neutrons and everything. So does that mean it's
Oh, okay. Let's do that. Let's do that kind of thing. Aluminum. Okay, let's take aluminum. Aluminum is what you call them? Column 13. Okay, what's his positive charge going to be? 3. Okay, what's the atomic number for aluminum? Okay, 13. And let's do the guy that's on the chart. What's his mass number? Do you know how to figure mass number? Mass number is going to be the atomic mass up there rounded. Okay, so we look at the atomic mass. It's 26.98. Essentially 27. Okay, we got to round it. And that's going to be the mass number for the aluminum dude whose isotope is on the periodic chart. Okay? So, when this guy forms an ion, he's going to be Al3+. Okay? Let's do the protons, neutrons, and electrons. How many protons? Let's see. He's still going to be 1327. Because when we form an ion, it doesn't affect protons or neutrons. It just affects electrons. Okay, how many protons do we have? Same as the atomic number. Very good. And how are we going to figure the neutrons? Subtract. Excellent. Okay, so this is 14. The 2 together should add up to 27, and we're good. And what are we going to have for electrons? Yes, we're minus 3 of the electrons. Very good, Linda. So we're down to 10. Yeah. Raise your hand if you didn't see how we did this. This is really, really important. This is big stuff. This is very, very, this like basic stuff that nothing else works if you don't know. Okay. So we're good here? No one has any questions? Okay. Did it count? Yeah. Okay. Good. Let's go on. While we're in this area, there's sometimes where you're going to want to know something about whether these little dudes bip around in pairs or singles. If you want to copy this down, this will tell you all the dudes that bip around in pairs. No on. Now, on has nothing to do with this, except to make it sound like a campaign slogan. No on 17. Nobody vote for 17. No. No on 17. What does that mean? Nitrogen, oxygen, hydrogen, and everybody in column 17. Now, that's all the guys that bip around in pairs. All of the atoms, and let's say this more scientifically, that form diatomic molecules. They bip around in pairs. That's my way of saying it. You have to go?
Yeah, where did it go?
What?
Remember you told me I had to go somewhere?
Oh, yes, you were supposed to clean it up. Yeah, 1117? Yeah, I think that was it.
Sorry.
Oops. Yeah, that's just right back here. Behind the building. That's the old F building. Used to be called F building. 117. Okay, now, that means that nitrogen is going to look like what? How are we going to write nitrogen? Like that? Nitrogen gas. N2. Oxygen, because all of the atoms that form diatomic molecules. That's what this means. Okay? It always works better with an example, doesn't it? Yeah. Okay. How are we going to write oxygen? O2. How are we going to write chlorine? Cl2. Yep. And how are we going to write iodine? Ooh. Oh. Knocked off my... No. I2. Okay? And so this guy's I2. And anybody in column 17, anybody that is nitrogen, oxygen, or hydrogen, H2, okay, they bip around in pairs. They form, that's called diatomic, di for two, atomic for atoms. So diatomic molecules are molecules that have two atoms. All of them are 17. All of them in 17 are diatomic. And you'll need to know that to answer some of the questions in the CSTs. They'll ask you questions that are going to require you to know that kind of stuff. Okay, are we good? Did that take care of this sheet for you? Okay, terrific. Now, in number 1 through 15, did you folks all do that? How many of you did that? Did you go to the CST online where I showed you to go?
Oh, yeah, I would do that.
Good. Okay. Let's look at them. Let's go to here. Let's go back here. Okay. Learning Center test quiz reviews in my website. Down at the bottom, this little dude right here, CST release questions, State of California. When you click that baby, this is where you're going, and you want to go down until you get to questions. And questions are going to start here, I think, on page 9. Yeah, there it is. Okay. All right, there we go. So, did anyone who reviewed this have a specific question that they were having trouble with? Number 10? Okay, let's go down and take a look at number 10. Let's get this recorder thing out of the way. There we go. Number 10. Oops, back up one. Okay, here's number 10. All right. Now what you want to do is get out your periodic tables, and let's look and see why it is what it is. Which of the following ordered pairs of elements shows an increase in atomic number but a decrease in average atomic mass? That's weird, isn't it? That's very weird. Okay, and the answer here was cobalt and nickel. And why is that? Look at the mass of cobalt. What is that? 58.9. And what is nickel? 50, not much, is it? 58.6. Okay, but it does go down. Very, very weird. That has to do with the neutrons, okay? And when they say the atomic number increases, that means that from here to here we're getting an increase of 1, which means we have one more what? One more what? Proton. One more proton, and when we add a proton, instead of having cobalt, we have nickel. Okay? Usually there will be neutrons added as well. In this case, I believe there's a couple of neutrons down for the nickel. You could figure that out pretty easily by figuring out the mass number versus the atomic number, and then just subtract it out, and you'll see the neutrons are probably 2 down. I haven't worked that out, but my guess is that that's the case. Time goes fast when you're having fun. Did I answer your question? Okay, good. And so what you want to do tonight or over the weekend, 16 through 30, right? Okay, we'll see you on Monday. I hope you're finding this beneficial.